Across major technology and financial firms, the race to deploy enterprise AI is consuming massive amounts of capital and engineering bandwidth. Many technical product managers operate under a specific assumption. They believe that fielding a successful AI product is primarily a matter of selecting the most intelligent API available or training a model on proprietary corporate data. The reality in production is entirely different. Deployments utilizing the most advanced frontier models available are actively draining entire corporate budgets, failing to show measurable ROI, or losing benchmarks against generic chatbots. This exact paradox struck three highly sophisticated enterprise giants: Uber, Bloomberg, and Morgan Stanley. On the surface, their rollouts featured massive user adoption rates and models trained on billions of parameters. Beneath that surface, severe architectural vulnerabilities dictated the actual results. We can trace these vulnerabilities to three distinct constraints in production AI: agentic token economics, fine-tuning decay rates, and retrieval infrastructure. In an enterprise environment, a system's architecture dictates its survival. The raw intelligence of the underlying large language model is only a fraction of the equation. In December 2025, Uber launched Claude Code, an AI coding assistant, to its engineering organization of roughly 5,000 developers. On paper, it was a massive product success. Adoption scaled rapidly. Within 4 months, 84% of engineers were using the tool, and the company reported that 70% of all committed code was AI-generated. The immediate financial consequence of that success was severe. By April 2026, just 4 months into the rollout, Uber had burned through its entire AI budget for the year. Standard software budgeting operates on a linear per-seat model. A company expects to pay a flat subscription fee, which for enterprise tools typically caps at roughly $150 to $250 per user each month. We are plotting the flat linear SaaS budget line against the reality of agentic token burn, which forms a sharply exponential curve. This growth is driven by token multiplication. It starts simply. A user issues a single task prompt to an agent. The agent enters a multi-step reasoning loop. It sends a query, receives an answer, and formulates the next logical step. At every step, the agent appends the entire previous conversation history and resends that accumulating text block to the model. This recursive data transfer means a single user task multiplies token consumption exponentially compared to a simple chat exchange. Because Uber's architecture lacked built-in spending ceilings, the financial fallout scaled with the tool's adoption. Power users were suddenly consuming between $500 and $2,000 per month in tokens. To compound the issue, Uber's executives admitted they could not draw a clear line between this massive internal token spend and any corresponding improvement in consumer-facing business results. High adoption metrics are irrelevant if the underlying unit economics are flawed. Failing to architect for non-linear token economics turns a successful product rollout into an uncontrolled financial liability. 2 years earlier, in March 2023, Bloomberg announced a different approach. They decided to build a custom language model, trained specifically for finance. The investment required massive upfront capital and compute. Bloomberg GPT featured 50 billion parameters, trained on a mix of public data and over 360 billion proprietary financial tokens. The training process alone cost an estimated $3 to $10 million. The strategic premise was common in enterprise AI at the time. Pairing proprietary corporate data with dedicated from-scratch training inherently creates a durable competitive advantage. Upon release, the premise seemed validated. Bloomberg GPT successfully outperformed the similarly sized open-source models available at that time on finance-specific tasks. However, Bloomberg's original paper omitted a critical data point. They did not directly benchmark their custom model against frontier models like GPT-4. This chart displays findings from independent researchers at Queen's University, who ran the direct comparison on the FinQA benchmark. Bloomberg GPT scored 43%, while GPT-4 reached 68.79%. GPT-4 achieved a nearly 26-point lead on a specific financial benchmark, possessing zero specialized financial training. This performance gap exposes the flaw in custom training, a concept known as fine-tuning decay. Custom training freezes a model's knowledge as a static snapshot in time. This timeline graph illustrates the decay. The static state of Bloomberg's custom model capability forms a flat horizontal line. Against that, we plot the continuous advancement of general-purpose models as an upward trending curve. As general models advance, the capability gap that originally justified a multi-million-dollar custom training investment rapidly narrows and eventually vanishes entirely. Proprietary data is valuable, but baking it directly into a model's weights is brittle. Overinvesting in static, custom model training is a losing bet against the relentless evolutionary pace of general-purpose APIs. Morgan Stanley provides the countermodel. They successfully deployed an AI-powered internal research assistant for their wealth advisors. Rather than spending millions training a model from scratch like Bloomberg, Morgan Stanley directed their engineering resources toward meticulously organizing their internal data. The scale of this knowledge base was immense. They launched with over 100,000 internal research documents, eventually scaling the corpus past 350,000 files. Asking a generic LLM to rely on its internal memory to recall specific financial details guarantees high hallucination rates. The model will confidently invent facts it cannot retrieve. This schematic maps out their solution, a retrieval-augmented generation, or RAG pipeline. In the embedding phase, a user query is converted into a mathematical vector to scan the massive document database. Next is the critical retrieval action. The system isolates only the highly relevant internal documents based on strict mathematical vector matching, ignoring the rest of the corpus. Finally, in the augmentation phase, these retrieved factual documents are packaged alongside the user's original prompt before the query ever touches the large language model. Morgan Stanley spent months curating this pipeline. They used human experts to rigorously test responses, explicitly evaluating factuality and hallucination rates long before scaling the tool to users. This data readout highlights the exact metric that proves the architecture's value. Retrieval efficiency reportedly rose from roughly 20% to 80% after the RAG system launched. That massive jump in system accuracy was achieved entirely in the vector database and retrieval layer, independent of the baseline intelligence of the LLM. By establishing this robust, predictable pipeline, Morgan Stanley safely expanded their architecture in 2024, adding a second automated tool to generate meeting notes and follow-up actions from client conversations. In production environments, the underlying large language model is interchangeable. The data retrieval infrastructure is the most reliable lever for system accuracy and measurable ROI. Treating enterprise AI deployment like standard software procurement guarantees failure at scale. The budget models and infrastructure requirements are fundamentally different. Uber's rollout yields the first rule. You must engineer strict token metering and hard spending caps to control the non-linear cost of agentic reasoning loops. Bloomberg's multi-million-dollar training yields the second rule. You must assume the baseline intelligence of general APIs will quickly outpace static, fine-tuned custom models. This unified system architecture diagram outlines the mandate for technical product managers. You need a token metering firewall to limit cost, a dedicated RAG and vector database retrieval layer to secure facts, and a generic LLM API block to process text. Morgan Stanley's success confirms the final rule. Direct the majority of engineering resources and evaluation frameworks toward that retrieval layer, rather than custom model training. True competitive advantage in enterprise AI does not lie in the specific intelligence of the model you choose today. It lies in the resilient, highly controlled pipeline you build to manage it tomorrow.